Welcome to Chapter 4 lecture. We're going to talk about atoms and elements today. So, in this chapter, our focus is going to be particles and charge, the periodic table, and kind of some of the organizational schemes and some of the things that we can pull directly from the periodic table. We're going to have a challenge question associated with the periodic table that we'll go over in detail, and then general nomenclature, or how we talk about or abbreviate chemicals, mostly. So we talked a little bit about atoms in the previous chapter. We're going to talk a little more specifically about what atoms are, and what they make up, or what is made up of them, rather than just how we classify them. So we're going to go through a lot of examples. Here we talk about, atoms make up everything from the ground on your feet to, the air that we breathe, the smells in the air. Here we have a nice little picture in the atmosphere near a lake. We would have, maybe some oxygen and some nitrogen, which make up 90% of the atmosphere. And then over here, they're representing some trimethyl ammonia, or amine, which is present in fish, gives it that kind of fishy smell. This rock they're representing is some type of carbide, which is a common transition metal material. Lots of natural minerals are made of different carbides. So the book is going to give a whole bunch of examples about, how we can compare the size of atoms to this, or how small this is compared to something else. We're not going to really be focused with these kind of qualitative measurements. In chapters either 5 or 6, we'll do some mathematical, equivalences so that we can, talk about things precisely. But it's kind of interesting to see how the book relates the different sizes, if the atoms in a pebble were the size of the pebble would be larger than Mount Everest, little silly things like that. So, again, atoms compose matter. Anything at this point that's composed of atoms is matter. That's our definition. We're not going to be too concerned with the exceptions and other things like that. Elements are pure atoms. You can have an atom all by itself. That obviously has to be a pure element because only one thing by itself has to be perfectly pure. You can have a conglomerate of the same type of atoms that form a, substance, an elemental substance. If we mix atoms, then we get compounds or molecules, chemicals. So we do have some synthetic elements. These are the ones that are found at the bottom of the periodic table. All the other ones, occur naturally through the fusion of stars. The synthetic elements we use, we don't use them for anything really. I guess plutonium has been used historically as a weapon. But other than that, most of our synthetic elements kind of just exist for academic pursuit. Most of them have been made in Russia, where they have a very specific particle accelerator. Well, they'll accelerate two particles of specific masses near the speed of light and then collide them. Once they collide, they're able to actually fuse their nuclei for fractions of a second. Some of them it's picoseconds, some of them it's nanoseconds. It depends on how unstable the nuclei actually is. And so that's where we get all these synthetic elements. We don't have to be too concerned with that. So the book brings up a lot of names. I've mentioned this before. We'll talk about them, but you're not going to ever be responsible for any person's name, any dates, anything like that. It's interesting to know where some of the origins and history of this is, but that's about the only purpose of this. You don't need to be concerned with memorizing any of this. But Democritus, and this other person that I'm not familiar with his name or how to pronounce it, they were philosophers, and so they were kind of the first people to champion this idea that everything that we see around us can be broken up. And eventually, as we break it up smaller and smaller and smaller, we'll get something that we can't break up anymore. And this, in the Greek or Latin, was atomos, which we have translated to atoms, meaning indivisible. We know now that we can divide atoms up into their subatomic particles, and those subatomic particles can be broken up into fundamental particles. We'll only ever talk about the subatomic particles that make up atoms, and so that's going to be protons, neutrons, and electrons. And so the different combinations of those are what give us all our different types of atoms and elements. John Dalton, several hundred and, 1,000, a couple hundred years later, John Dalton was the first person who came up with an actual atomic theory. Previous, Democritus is just not really atomic theory, is just this idea that something indivisible exists. John Dalton kind of put some specificity on that, so he came up with the idea of the element, the tiniest indestructible particles, if they're pure, make up an element. All atoms of a given element have the same mass. And that if you combine these atoms in different ways, in different whole number ratios, you can't divide them any further, so they have to be in whole number ratios. You get compounds or chemicals or molecules. So this was pretty revolutionary at the time. You know, through modern advances, IBM was able to pay probably a pretty penny to have a movie made out of single atoms. Very cool academic pursuit, but useless in all purpose other than showing people that we can actually do it. So this is using the scanning tunneling microscopy that we've talked about. This is really the easiest and most accurate way, or not most accurate, easiest and most visibly distinguishable way to view individual particles. You have what's called AMF, which is a lot more accurate, but it doesn't look as pretty and it's a lot more difficult to do. All right, so moving on, after Dalton, we had J.J. Thomson. He came up with the idea of the electron. So we still don't know about the proton or the neutron, but he came up with the idea of the electron. And so he did some experiments that he basically was able to detect electric or negative charge in the nuclei, or not in the nuclei, but in atoms or in molecules. So he found out that electrons are negatively charged, and they're much smaller than the atoms that they're found within. And he found that they're distributed universally around the substance. We'll fine-tune this a little bit more, but this was a big discovery. He didn't find evidence of the proton, but if there's, a negative charge somewhere, there must be a positive charge canceling it out if we have neutral species. And so that's what we had. So he came up with this plum pudding model where the electrons kind of float around in a soup of positive charge. That was refined by Rutherford. And so what he did is he shot alpha particles, which are basically helium nuclei, through a piece of gold film. And so what he noticed is that most of the particles went directly through the film. And so this told him that if I'm shooting something at a solid and it's going directly through, that solid must be mostly empty space, like a meshwork. However, sometimes, very rare, he would notice scattering. So they would deflect off at some angle, or even, in some cases, shoot almost directly back at the source. And so this told him that there was some dense sphere of charge, of positive charge, that would deflect the alpha particles back. And so this was a very interesting experiment. And so he was able to, kind of see that this plum pudding model didn't make sense. If things were reflecting back, there had to be some dense, localized unit in the center of the atoms. And so he came up with the idea of the nucleus, which we know now as being all of the protons and neutrons packed together in a very dense central location that's surrounded by these electron clouds. So over 99.99% of all the mass of any atom is going to be localized in a very small point at the center of the atom. We know this as the nucleus. So Rutherford's came up with the idea of the nucleus, and that this dense nucleus was surrounded by negative charge, which was kind of in agreement with what we had seen before. He came up with the idea of protons. And so, again, we don't need to be familiar with this. It's just a very important experiment that kind of developed one of the crucial steps on our way to modern atomic theory. I think in next chapter, we'll talk about the next progression that will actually be a little bit more concerned with knowing the details of. So we can look through this again, not super important. 99% of the mass occupies only a small fraction of its volume. Again, same things we've said. More descriptions of how size and mass relate to real life objects. We're not going to be too concerned with this. What we can say is that everything that makes up the atom has mass. However, protons and neutrons weigh about the same, but a proton or a neutron weigh about 2,000 times more than an electron. For all purposes of calculations, that makes it less than 1% of the total mass. So it's not going to contribute meaningfully to any calculation. So we consider electrons to essentially have negligible mass. So we've mentioned this before, but we have or not our fundamental particles, but our subatomic particles, protons, neutrons, and electrons. These all have some associated charge with them. The electron has a negative charge, the proton has a positive charge. In elements, the number of protons and electrons are always equal to each other because elements are always neutral. If you have an ion, which is a charged particle, then you have uneven numbers of protons and electrons. This leaves neutrons. Neutrons are kind of the weird thing that we're not going to really talk about much. We can think of neutrons as the glue that holds the nuclei together. Isolated charge is not a stable thing. If you have a whole bunch of static electricity that builds up and you touch something, that static electricity will arc from you to whatever you're touching and dissipate. That's another example is lightning. I think we'll have a slide on that. Lightning is nature's biggest form of separation of charge. And so in general, charges want to attract each other. So when we have same charges, they repel each other. But the nucleus is a whole bunch of positive charge and neutral charge. The neutrons serve as the glue that kind of holds that together, and then the electrons kind of orbit the positive charge. We don't need to care too much about the physics of this. We just want to understand that, this doesn't quite make sense. One thing we notice as we go through the periodic table is as we get heavier and heavier, lower and lower elements on the periodic table, hydrogen's number 1, lead is somewhere down near 80. As we get towards the lower and lower elements, they tend to have more and more neutrons because their nuclei become less and less stable because of the abundance of positive charge in the nuclei. And so they need more neutrons to kind of serve as the glue to hold them together. So hydrogen doesn't have any neutrons. Helium has 2 neutrons and 2 protons. Lithium has 3 protons and 3 or 4 neutron or 4 or 5 neutrons. So they tend to have about a 2-to-1 ratio when it comes to neutrons to protons when you're in the early periodic table. But when you go to the lower end of the periodic table, it's closer to 3-to-1. And so this is just a concept of physics that we're not going to really get into. Something interesting to note, though. So we'll look at the actual masses of protons, neutrons, and electrons. And so you can see that electrons are incredibly tiny compared to protons and neutrons. Protons and neutrons are almost identical. And if you actually do the math, you'll see the difference in their mass is almost exactly equal to the electron. So one of the things that separates the proton from the neutron is a neutron is kind of like a proton and an electron combined in a very, very generalized sense. So their mass is all equal. We don't use kilograms for this because this would be a really awkward number to always be doing calculations. So we come up with the AMU. This is the atomic mass unit. It's just a devised unit for convenience of talking about things in whole number ratios. We only have protons and neutrons. You can't have half a proton. You can't have half a neutron. So it's very easy to communicate them in terms of just whole numbers. We consider the mass of a proton to be 1, even though it's slightly more because of, sophistication in our calculations. When we originally came up with these units, we probably couldn't tell to the same degree of significant figures. Now, we have a little bit more specificity, but we still just average these or approximate them as 1 AMU each. The charge is whole number units, so it's always plus or minus integer numbers. We can't have 0 if we have a neutral compound. If we have more protons than electrons, we'll end up with a positive ion. If we have more electrons than protons, we'll end up with a negative charge. So, like I had mentioned, electricity or thunder, lightning is the biggest example of dissipation of charge. So in the clouds, you have a bunch of static electricity. There's a bunch of dust up there, kind of the same as if you rub your feet on the carpet. The dust is kind of rubbing against each other up in the clouds, serves as their carpet, kind of holding it all there. The earth is made up of mostly metals, which tend to have positive charges in them. So the earth tends to build up a positive charge on the ground. Once enough negative charge is isolated up here, it's so unstable that it will arc, thousands of meters to go down to the ground and dissipate that charge. So, if we had a periodic table, we'd notice that the periodic table is completely aligned and organized in terms of its atomic number. So if we look at the periodic table, it starts with hydrogen, which is number 1, helium, which is number 2, 3, 4, all the way to 119, depending on what your periodic table is. This number is the atomic number. We use Z to represent the atomic number. The atomic number is always equal to the number of protons. So our periodic table is arranged by the number of protons in every atom. So that's a very convenient and useful organization tool, and we'll talk about that a little bit more and a little bit about the guy who came up with it. So we have helium has 2 protons. It's number 2 on the periodic table. Aluminum has 13 protons. It's number 13 on the periodic table. They both have very different numbers of neutrons, and so the protons plus the neutrons is how we get the mass number. The mass number, or the atomic mass, is this number that comes beneath. So when we have a periodic table, the atomic number always comes on top, Z, and the atomic mass always comes underneath. Your periodic table may or may not contain all of this information. Depends on how good the periodic table is. We have the chemical symbol. This is kind of one of our key pieces of nomenclature. We're going to want to be familiar with what at least the first 3 plus these 2, potassium and calcium, very common elements. We're going to want to be familiar with these first 3 rows plus potassium and calcium. Anything beyond that, if you remember them, awesome. You'll need to be able to find them on the periodic table. So if I say, find ruthenium, Ru, you should be able to, scan around and find Ru and be like, okay, this is what they're talking about. I have to do the problem with this metal. But I'm going to expect you to know the chemical symbols to the chemical names for the first 3 rows of the periodic table. So hydrogen through calcium. Those are what we're going to deal with 99% of the time in chemistry. So it's important that you're familiar enough with them that you can identify them when they're in use. So some of these, like potassium, is K. A lot of these come from the Latin. So there's a lot of different reasons for why we came up with different names. That's not important in knowing why or the history. It's interesting. It's unique. But we're not going to care about it in this class. So here's an example of a few in their Latin roots or origins where they got their chemical abbreviations. Some of them are based on their properties. So argon is a noble gas. We're going to talk about the noble gases and how they don't really do anything. So historically, we like to make jabs at nobility because they didn't do anything productive. And so chemicals that didn't do anything productive or never changed were inactive. We called noble whatever they were. So we have the noble gases, which is a group on the periodic table. We have the noble metals, which is things like gold, silver, and platinum that don't tend to tarnish or react with things very well. Bromine comes from, its Greek word in stench. Bromine is a very nasty liquid that very readily turns into a gas. It's pretty toxic and can hurt you pretty bad if you don't handle it in a fume hood. So some are named after places, some are named after people. All fun and cool stuff. So the periodic table has a specific standard. every periodic table is going to be slightly different. So this one doesn't have mass numbers. It also doesn't have the names, but it has some fun pictures. Every periodic table is going to be a little bit different. The one thing every periodic table will have is the atomic numbers, the numbers of protons, and the chemical symbol. Those are the only things that are required in a periodic table. So you kind of have to fill in the blanks sometimes. This periodic table that we have is not how we've always had it, but the person who is responsible for its kind of inception is Dmitry Mendeleev. He was the first person that really saw a pattern in the properties of elements and arranged elements according to their properties. We can summarize these patterns or these periodic properties as periodic law. Anything that's periodic is something that happens repetitively. A period is the unit of time that it takes for something to repeat itself. So if I have a circle, the time it takes me to go one revolution around that circle is considered one period. Periodic law is the laws that we understand from the different groups of elements. So all of these colored coordinated elements tend to have the same properties. So helium behaves very similar to neon, which behaves very similar to argon. Beryllium behaves similar to magnesium as calcium. Originally, he had just laid all these out, color coordinated them. We've adapted this to be a little bit more vertically oriented with columns and rows. We'll talk about this, but in generally, down a column, which we more often call a group, we have similar properties. So everything in group 1, hydrogen's kind of the special exemption. But lithium, sodium, potassium, rubidium, and everything else, they all have very similar properties, which are different than the properties of group 2, which are different than the properties of group 9, which are very different from the properties of the noble gases, which are the very last group on the periodic table. So he came up with periodic law and was basically able to give us a more convenient way of grouping our chemicals based on how they behave. So if you've worked with one chemical, say you've worked with sodium before, but you've never worked with potassium, well, you know it's going to behave very differently. And based on periodic law, we know that as we go lower and lower on the periodic table, chemicals tend to be more and more reactive. If they're on the left side, if they're on the right side, they tend to be less and less reactive as they go down the periodic table. So if I'm on this side, I know that as I go down, they become more reactive. So if I've worked with sodium, but I have to work with potassium now, I know I need to be a little bit more careful, but it's essentially going to behave the same. And so this is one of the benefits of having these periodic laws and periodic trends, is we can infer a lot of useful information. Okay, so we can break up the periodic table into a bunch of different classifications. We have, most simply, metals and everything else. We have the metals, which is broken up along this diagonal. If all you remember is that everything to the left of this little cutout, so, we have the periodic table, it comes here, and then it cuts out, and then it comes back up. If we just remember at this cutout that everything to the left of this cutout is a metal, that will serve us for 99% of the time. If we want to remember specifically, metals are everything to the left of this jagged box. That's basically everything on the either side of this jagged line. And then the non-metals are on the other side of the box. The metalloids are kind of in between, depending on what conditions you put them in, really high temperature or really low temperature, really high pressure or really low pressure. They might behave like a metal, they might behave like a non-metal. The non-metals essentially behave not like metals. So we define how metals behave, and then non-metals just do the opposite. So metals, hopefully some of this is familiar, things that you know or have seen before, minus maybe the electron thing. So good conductors, they conduct heat and electricity. They're malleable and ductile, which means that they can be formed into different shapes, either flat sheets or wires. These aren't one and the same, but they're usually synonymous. Most materials that can do one can do the other. And they're often really shiny in their pure states. If they're in mineral state, they're not necessarily shiny, but in their pure states, they're very shiny and reflective of light. They tend to lose electrons. So, like we said, metals tend to be positive. The reason this is because they lose their electrons. If you lose the negative charge in you, you're going to become more positively charged. Or vice versa. If you lose the positive charge in you, you'll become more negatively charged. So, metals, iron, magnesium, sodium, gold, all of these are. Non-metals are things that are on the opposite of that zigzag. You can, refer back to this image. Lots of periodic tables will actually color coordinate these things, so it's nice, and then they'll give you a little key. Non-metals behave the opposite. So, and they're very disparate in their generalized properties. So we don't quantify them as much. They do have poor conductors. They tend not to be malleable or ductile. And they tend to gain electrons. So, and those are the only specifics about nonmetals. What they look like, how they act otherwise is pretty hard to pin down. That's why we have the groups and we can associate every group to their behavior. So they tend to gain electrons. If they gain electrons, they're going to become negatively charged. So metals lose electrons, become positively charged. Nonmetals gain electrons, become negatively charged. It's very common for metals and nonmetals to form compounds or molecules together because the positive and negative charges will cancel each other out. Metalloids lie along the middle between the two and behave like either one depending on their conditions or their composition. So semiconductors are probably the most famous and most useful version of metalloids. Silicon is probably the number one semiconductor or metalloid that we use. It's used in some semiconductors, but it's also used in all of our computer chips. So very important things, but depending on how we treat them, they can behave like an insulator or a conductor. They can behave like a metal or a non-metal. So, like we said, silicon is very important in the semiconductor industry and just computer chips in general. As well as germanium, they're starting to do a bit of computer technology with germanium, but it's not as earth abundant. It has some very interesting properties, but silicon is incredibly earth abundant. All right. So here's where you really want to, take a picture or copy this slide. This is the first of the two slides. This is the second one that we'll cover related to the challenge question. So the challenge question is going to be filling out this periodic table. I'm going to have black boxes here, 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 and here. What you're going to have to do is fill in all of these naming conventions. So I want you to know what I mean when I talk about certain things. I'm going to refer to things as the main group, as the alkali metals, the alkaline earth metals, the transition metals, the halogens, the noble gases, or the lanthanide and actinides. We're not going to deal much with the transition metals or the lanthanide actinides. We're going to deal a lot with the main group. The main group is everything that is not... The book calls them transition elements. No one who is a practicing chemist will ever call them transition elements unless it's a language thing. They're called transition metals. They are all metals. They're called transition metals. You will be required to memorize what the main group is. In terms of the main group is everything that is not the transition metals or the lanthanide actinides. So the alkali metals, the alkaline earth metals, groups 3A through 6A, the halogens, and the noble gases are all the main group. They all have very predictable properties based on where they are at in the periodic table. That's very important. Main group behaves much differently than transition metals, which behaves much differently than the lanthanide actinides. So we want to break those three different behaving groups apart. Besides that, we have 4 different groups be, besides the main group, which is everything other than the transition metals and the lanthanide actinides, we have a couple groups that we're going to use excessively. The alkali metals in group 1 are incredibly important. So are the alkaline earth metals. Alkaline earth metals is longer than alkali metals. Group 2 is 2 is bigger than 1. That's how I always remembered it when I was first learning, and it was a memorization rather than just something that was natural. The halogens are also another important group. So if you think about like minerals and nutrition or biology and things that you've heard of a lot, you've heard a lot of lithium, sodium, potassium, calcium, magnesium, fluorine, chlorine, maybe bromine and iodine. These are very, very important molecule or atoms in biology and nature. They have high relative abundances. We're going to talk about them a lot. So I'm not going to talk about them specifically. I'm going to say an alkali metal can react very readily with a halogen because of this. Alkaline earth metals tend to have this type of charge because they're in this position. The noble gases are kind of our ideal. They are incredibly stable, and every other atom, every other element on the periodic table wants to achieve the same stability that these noble gases have. These noble gases are almost never, you can't do anything with them. Xenon and some of these heavier ones, if you get into a laboratory with fancy conditions and lasers and all sorts of nonsense, you can get them to do some stuff. But helium, neon, and argon, there's absolutely nothing you can do with them. They're rock solid. Doesn't matter how hot you heat them, what chemicals you put at them, they just don't react. They're so stable that they're just happy to be all by themselves. Every other chemical wants to achieve that same stability, and we'll talk about that a little bit. But this is what you need to memorize, and we'll need to fill out for the second challenge question on exam 1, which will not be next week, but will be the week after. All right, so like we said, all the groups in the main group have very predictable properties. So alkali metals, group 1, the first one that I want you to memorize, they're incredibly reactive. All of these, if they encounter water, will either catch fire or just spontaneously explode. As you go lower and lower on the periodic table, they tend to be more and more reactive. The reason for this is these chemicals. So if we go back, lithium compared to helium is just one position away. If I move from helium to lithium, I just increase by 1. There's something really special and stable about the number of electrons that the noble gases have. That's what makes them so stable, is their number of electrons. So helium has 2 electrons, neon has 8 more electrons, argon has 8 more electrons, krypton has 16 more, 16 more. Now they have 22 more, or 32 more, and so forth and so on. So this is related to how far down the periodic table they are and how the electrons group. But ultimately, you'll notice that the number of electrons increases by how many molecule or how many elements are in each row of the periodic table. So in the first row, I have 2, so there's only 2. In the next row, I have 8. 1, 2, 3, 4, 5, 6, 7, 8. So it increases by 8. Once I get down to the transition metals, it increases by another 10. Once I get down to the lanthanides and actinides, it increases by another 14. This is just something that we'll get into more a little bit later. But what we want to focus on is that lithium is just 1 away from helium. So all it has to do is give up 1 electron, and now it's in this special happy configuration, this happy stability. That makes it a lithium ion, and now it's a charged particle, which isn't as stable, but getting this electron configuration is the number 1 goal. Next is neutralizing their charge, and then we'll have chemical compounds that bond together. But in general, all the alkali metals will give up 1 electron. It's really easy for them to just throw off 1 electron and have their perfect configuration. And so that's why all of these are really reactive. The alkaline earth metals want to do the same thing, but since they have to give up 2 electrons, giving up 2 electrons versus giving up 1 electron creates more positive charge in the nuclei, or more isolated charge that isn't evened out by the electrons. So these don't happen quite as fast. They're not as reactive, but they're still pretty reactive. Magnesium and calcium, if you put them into water, will just start to boil and generate hydrogen gas, which can then catch on fire. Halogens are also very reactive for the opposite reason that the alkali metals or the alkaline earth metals are very reactive. They're one position away from the noble gases, just like the alkali metals. And so instead of losing 1 electron to get to that noble gas position, they can gain 1 electron and have that same number of electrons as its relative noble gas. So these things will rapidly gain 1 electron, usually from an alkali metal. Alkali metals want to give up 1 electron. Halogens want to take 1 electron. That's why things like sodium chloride, table salt, are so common in nature, is because they're both really reactive elements and they're perfect matches or perfect partners for each other. The noble gases are incredibly stable because they have the perfect number of electrons given their energy level, which the energy level is determined by what row of the periodic table they're in. So if we go back here, we have the first row, the second row, the third row. Every time the row increases, the energy increases. And so the number of electrons is particular to each energy level. At the first energy level, we can only have 2 electrons. At the second energy level, we can have 10 electrons, so on and so forth. So the noble gases are kind of our poster child. We are always trying to get to their electron number, or configuration is what we call it. So I've mentioned this a couple times, but we gain and lose electrons to form ions. If I gain something that's negative, if I add a negative number to something, it becomes more negative. If I take away a negative or I add a positive, I become more positive. So if I lose electrons, I become more negative. We call this, if I lose electrons, we become more positive. We call this cations. So whenever I lose electrons, like in the case of sodium, potassium, the alkali metals or the alkaline earth metals, they're going to become cations. The halogens, which always gain 1 electron, they're going to be anions. They gain 1 electron, so they become negatively charged. We call them ions generically. Cation specifies that it's a positive ion. Anion specifies that it's a negative ion. The way we represent this, in addition to our chemical symbols, is as a superscript. We put the number first and then the charge. So this would be considered a magnesium 2 plus, or a positive 2 magnesium ion. It has a positive charge of 2. Where this would be an oxide, I don't call it an oxygen ion. We have special naming for it that we'll go over in a little bit, but this would be an oxide ion. So this is oxygen 2 minus. If you look at your periodic table, oxygen is 2 groups away from the noble gases. It wants to gain 2 electrons so that it can have the same number of electrons as the noble gas that it's nearest to. Magnesium is nearest to the noble gas the other direction, so it'll lose 2 electrons, become positively charged to get to its nearest noble gas electron number. These two things could combine together to make magnesium oxide, which would be a neutral compound. They both have their ideal number of electrons, but they're also neutralized out, so they don't have that separation of charge that we've talked about as being unstable. Superscripts mean charge. Subscripts, or leading coefficients, mean the amount of. So if I had a 2 down here or a 2 in front, that would mean I have 2 oxygen atoms. This means in the superscript that I have a specific charge, a negative 2 charge or a positive 2 charge. So we can write ion forming or ion quenching as a chemical reaction. Remember, we have starting materials or reactants. We have a reaction arrow that leads to our products. If we do let's say the reaction in a cell phone battery or a lithium ion battery, we take lithium metal. That lithium has one more electron than its nearest noble gas, so it wants to give up one electron so that it can be a little bit more stable like its noble gas is. So lithium will give up one electron, and so the products are a lithium cation and one electron. This one electron is what powers all of your electrical devices. Now, it's not just one electron, it's thousands and thousands of millions of electrons over a very, very quick period of time. But that's not important for us. That's an engineering thing. So, in general, the number of protons minus the number of electrons gives you your charge. If you have more electrons than protons, that'll give you a negative number. If you have more negative charge than positive charge, you should have a negative charge. So in this case, we have 3 protons minus 2 electrons gives us a positive 1 charge in lithium. And so that makes sense. Lithium should be plus 1 if we lost 1 electron that has a charge of 1. Remember, in chemistry, we're always going to use whole numbers for all of our observable things. Protons, electrons, molecules, chemicals, things like that. So we could go the other way, where we do, an ion, where we take an element plus an electron, and it becomes an ion. So if we took lithium and fluorine together, lithium would give up its electron, fluorine would take the electron and become fluoride. Again, we'll go over this naming procedure in just a second. But same idea. If we give an electron to fluorine, it's going to have one more a negative charge than it has positive charge. So protons minus electrons will give us negative 1. If you did an ion charge calculation like this, you don't have to put the minus in the superscript. You could put just negative 1. But when it's on a chemical, like oxygen or oxide, you need to put the 2 and then the minus sign, or the 2 then the plus sign, both in the superscript. For a mathematics problem, that's subjective. So we could have a lithium cation and a fluorine anion or fluoride anion. The general rule for naming is that the cation just keeps its name. We don't change anything. Lithium becomes a lithium ion. However, the anion gets a little bit different of a treatment. So what we do for anions is that we cut out the last 2 vowels. So in fluoride and fluorine, it would be INE. We cut out the INE and put IDE. For the case of chemistry, Y is a vowel. So AE, IOU, and Y are vowels for the case of this rule. Fluorine, so yeah, we don't have fluorine, but if we go up here, so fluorine, we cut out INE and we replace it with IDE. Oxygen becomes oxide, chlorine becomes chloride, so forth and so on. All right. So we kind of talked about this, and that every group has, its ideal number of electrons that it has. And so what we call that is the valence electrons. The valence electrons are the outermost electrons. So if we go back to the periodic table from before, we have these different levels. I called them energy levels. We can also call these valence levels. Valence is a very weird term. I'm not sure what the origin of it is. I probably should, but I don't. But it just refers to these energy levels. So the first energy, or the first valence level, is lower in energy than the second valence level, than the third valence level, than the 7th valence level. So, which makes sense. As we go down the valence levels, or we go down the energy levels, we go down the rows of the periodic table, we're adding more and more particles. So we're adding more neutrons, we're adding more protons, we're adding more electrons. Even though these are generally neutral, as we get more and more protons in the nuclei, there's really more and more isolated charge that is then kind of counteracted by the isolated electron cloud that surrounds it. That's still not perfectly stable, and it requires more and more energy as we push more and more of these charged particles into the the atom, the nuclei, and the electron cloud. So we have a general rule that we call the octet rule. Because for the main group, we notice that stability is optimized by having integer numbers or integer multiples of 8. So for the minus the first row. So the first row only has two elements. It has hydrogen and helium. We call that the duet. Every other one we call the octet, because every other main group valence level has an octet of electrons that leads to the next energy level. So we fill up 8 electrons, and this makes sense. So if we go through the main group, 1, 2, 3, 4, 5, 6, 7, 8. And that's true because, again, the main group, we cut out the transition metals and the lanthanide actinide, so there's always just 8 essential electrons in every main group valence shell or valence row energy level. These are all synonymous terms that you should be comfortable with. You don't need to use them yourself, but you need to understand them when I use them. Okay. So we're going to talk exclusively about valence electrons. We don't ever care about the electrons that aren't in the outermost level. And so those are our valence electrons. They're the highest energy electrons. All the electrons that are underneath the valence electrons are so low in energy that they're incredibly stabilized because they already, fulfill the previous octet, the previous noble gas configuration. And we're going to really hammer this out and nail it down, the specifics of valence electrons, why they do these type of things in the next chapter. We're just kind of introducing it so that you can get familiar with some of the terminology. So ions, because of their relative position to the noble gases, we can have pretty good predictions on what their ion charges are going to be. So the alkali metals are always just one away from the previous noble gas. Lithium can lose one electron to become lithium ion, and it has the same configuration as helium. Sodium element can lose one electron, become sodium cation, and have the same configuration as neon. On the other side, fluorine or oxygen or nitrogen or any of these other can gain a certain amount of electrons, basically however many positions they are from the noble gases, they can gain that many electrons to get the noble gas configuration. So iodine, bromine, chlorine, fluorine, the halogens, will all gain one electron, become an anion, and then have the noble gas configuration, that optimum stability of electrons. Group 6A, oxygen, sulfur, these need to gain 2 because they're 2 positions away. Nitrogen would need to gain 3. Group 3A, you'll notice they're not quite gaining enough to get to the noble gas configuration. Group 3 is a special case. Group 3 doesn't have to have a full octet. And there's a reason for this that we'll be able to explain next chapter. The ones that they don't have filled in are ones that have variable charge. But in general, anything from group 3A to 5A can have variable charge. Like nitrogen is almost always 3 minus. However, when nitrogen is bonded to oxygen, which is a very common thing that we'll deal with, nitrogen becomes positively charged. Oxygen is closer to the noble gas, so oxygen gets to go to the right, but if oxygen and nitrogen bind, oxygen goes to the right, nitrogen has to go to the left, because for oxygen to go to the right, it has to gain electrons. Well, it has to gain electrons from something. So if oxygen is gaining electrons from nitrogen, nitrogen has to lose those electrons and go the other way. So instead of being -3, it would be +5. We'll go over this variation, but in general, groups 1 and 2 are always +1, +2. The alkali metals are always +1. The alkaline earth metals are always +2. The halogens are always -1. Group 2, well, we'll say oxygen. Oxygen is the only other element that we can guarantee what its charge is. Oxygen is always -2. Sulfur is variable. Selenium, tellurium, these are all variable. Nitrogen is -3 or +5. Everything in group 4 is +4 or -4. Everything in group 3A is +3 or -3. And we'll get into these a little bit more when we talk about oxidation states and things like that. So isotopes. At this point, we've been saying that, all atoms are the same, which is true. An atom of oxygen is an atom of oxygen. There is no different. However, we have different types of oxygen atoms. What makes oxygen an oxygen atom is the number of protons. Oxygen has 8 protons. Everywhere in the universe, oxygen has 8 protons. But sometimes when oxygen is being made, when it's being fused in the stars out in the universe, that's how elements are made, is from the fusion of hydrogen, which turns into helium. Helium can then fuse with either another molecule of hydrogen to make lithium, or it can fuse with another molecule of helium to make beryllium. And so it goes through this process of fusing all these elements to make other elements. Sometimes, depending on how things fuse and break apart, oxygen gets made with 8 neutrons. Sometimes it gets made with 10 neutrons. Sometimes it gets made with 7 neutrons. There's all these variability of the amount of neutrons. This doesn't affect the properties of oxygen very much. So oxygen with 7 neutrons doesn't behave very different than oxygen with 8 neutrons, which doesn't really behave much different than oxygen with 10 neutrons. They all behave very identically. However, because the number of neutrons is different, their mass is slightly different. And so the way they interact with gravity is slightly different. That's the biggest difference between isotopes. Isotopes are elements that have different number of neutrons. And each isotope has its own natural abundance. So there's always, or almost always, some cases it's 50-50, but almost always there's a predominant isotope. The best example is hydrogen. Hydrogen is 99.99% hydrogen with just 1 proton and 0 neutrons. However, there is a decent amount, about 0.02% of hydrogen that has 1 neutron. And then there's a really, really small percentage of hydrogen that has 3 neutrons. They all behave very similarly, except for the hydrogen with 3 neutrons is actually radioactive. There's too many neutrons in that nuclei, and the glue is too overpowering, and it kind of leaks out in a matter of speaking. So here's an example with neon. We have neon 20. 10 neutrons, neon 21. This is how we represent isotopes, is we put the chemical symbol followed by a dash and the mass number, not the atomic number, because the atomic number for neon never changes. It's always 10. Neon is chemical 10, atomic number 10. However, its mass number depends on its number of neutrons. So we put the mass number behind it to designate which isotope it is. So we have 3 isotopes of neon. However, 90.5% of neon is all neon 20. That is overwhelmingly the major contributor to the natural abundance. However, about 10% of it is neon 21. So that's a decent, about 10% abundance of something with 1 extra neutron. However, neon 22 is pretty rare with less than 1%, a little more than 0.25% of the relative abundance of neon is this extra 2 neutron neon, or neon 22. What's on the periodic table, so if we scroll way back to your periodic table, or if you look at a periodic table near you, we got to go way back because we don't have a good periodic table for a while. So we go to this periodic table, you see that all these are decimals. However, AMUs, we just cut off at 1. A proton weighs 1 AMU, a neutron weighs 1 AMU. The reason we get these decimals is these are what we call weighted averages. So we take the average of all the isotopes respective to their abundance. So, try to get back to this. So we would take the mass of neon 20 times its relative abundance, the mass of neon 21 times its relative abundance, the mass of neon 22 times its relative abundance, and add all 3 of these numbers together to get the average mass of neon in the universe or in the world or within the sample that we're concerned with, whatever your viewing spectrum is. So, mass number. Some books call mass number A, some books call mass number X. Z is always the atomic number. Mass number is always going to be the larger number. So just remember, protons is Z, the atomic number. Mass number is the other number. It's the sum of the protons and the neutrons. So we have something like this, where we have a mass number on top and an atomic number on bottom, and the chemical symbol. This is a very particular way to represent isotopes. It's just a different notation. You'll notice this is different than the periodic table, where the atomic number goes on top and the mass number comes on bottom. This is just a notation for isotopes, not for the periodic table or chemicals in general. So a more easy way to represent these is just the chemical symbol or the chemical name and the mass number. Because really, the 10, the atomic number, will never change. It's always the same. So this is what we talked about, calculating the average atomic mass, or a weighted average. We take the fraction of one isotope times its relative abundance, or its percentage. Its percentage times its mass. I did that backwards. Take plus the percentage of the second isotope times its mass, plus the relative percentage of the next isotope times its mass. And you do that for every isotope you have, and you add them all together. The most important thing is that all of your fractions add up to 100, or add up to 1. 100% is equal to 1. So here would be an example. We could take with chlorine, we have this amount of percentage of chlorine times chlorine 35. This percentage of chlorine times chlorine 37 gives us the average weight of chlorine that we observe in the sample. So we could do the same thing with gallium. In this case, we have our percentages, and we want to figure out what the average mass is. So there we go. We put them together and do the same thing. Relative percentage times mass, relative percentage times mass, add them together, and we get the answer. So we can round to sig figs. We're not going to be concerned with sig figs in this. If we need to be concerned with sig figs, I'll tell you. It's a good practice if you want to always keep it handy, but it's not necessarily unless I tell you. All right, so last thing we're going to really talk about is radioactivity. So we're not going to get into the weeds. We'll talk about this a little bit more later. There's a whole bunch of different types of radioactivity and the types of radioactive decay. Essentially what radioactivity is it's the energy released when an unstable nuclei breaks apart. So when we have nuclear fission is the breaking part of the atomic nuclei. And when we break apart this nuclei, some amount of energy is actually released. Remember, we had mentioned that energy is related to mass and that E equals mc squared, where c is the speed of light squared. So that's a pretty fast and big number. So mass gets scaled to quite a lot of energy. So even if a tiny, tiny, tiny fraction of mass is lost, a whole bunch of energy is generated. And so when you have not enough neutrons to hold together all the protons in the nuclei, the protons will eventually break apart in some manner. Depending on how unstable the nuclei is, different things can fraction off. Sometimes you'll have an alpha particle or a beta particle or maybe even a gamma ray, depending on how high of the energy that is being released. These all lead to different types of radioactivity, which high energy can then damage things. This is why radiation is bad for us. So, in general, we talked about the atom. We're not going to be concerned with any of these people or their theories. Rutherford was a really big step forward from Dalton, where we were really able to determine these subatomic particles. Subatomic particles we do care about. We talk about them in a relative mass, the atomic mass unit, because it's easier to equate them because protons and neutrons weigh the same and electrons have negligible mass. So it's just easier for mathematics' sake to talk in AMUs. Protons and electrons are where all the charge comes from. A proton is our +1 or positive charge. Our electron is our -1 or negative charge. Again, these are equated charge. This is not like if you've taken a physics or an engineering or electricity course. This is not like 1 coulomb or something like this. This is, 1 atomic charge unit. Again, since protons and electrons have identical magnitudes of charge, we just equate them to each other. And so you can relate this charge to volts or coulombs or things like that if you want to. We'll do that later. So subatomic particles, neutrons have no charge. They kind of work as the glue that holds everything together. So you need to have the right amount of glue. If you have too much glue, the glue is going to leak out. And then if your glue or the neutrons is leaking out of the nucleus, that means your nucleus is breaking apart. If you don't have enough glue to hold your nucleus together, your nucleus is going to fall apart, and that's bad. So we need to have the right number to stabilize our nuclei. Periodic table, we have that challenge question that I'll review here in a second. But be familiar with, the main group, the alkali metals, the alkaline earth metals, the transition metals, the halogens, the noble gases, and the lanthanide and actinides. Being able to predict how many electrons are lost or gained. Atomic number is Z. Atomic number is always equal to the number of protons. This is how the periodic table is arranged. Ions are what happen when we have charged particles. So charged particles are created by the loss or gain of electrons. If I gain an electron or if I gain a negative particle, I'm going to become more negative. If I lose a negative particle or lose an electron, I'm going to become more positively charged. Positive ions are cations, negative ions are anions. Isotopes are elements that just have different number of neutrons. Depending on the number of neutrons, we can have either increased or decreased stability. Usually these extra or less neutrons don't have a big impact on the chemical as a whole. The big things we want to focus on is charge and particles, the periodic table, how it's organized, why it's organized that way, and what we can figure out from it, and our nomenclature. So going back to the challenge question, sorry to scroll so quickly, we're going to label the main group. The main group is going to be right here where it says group numbers. There's going to be a black box. Then you're going to fill in all these other boxes with exactly what's there. They're going to be black boxes. You're going to have a word bank that says main group. Main group's going to go right here. It's going to say alkali metals, alkaline earth metals, transition metals, noble gases, halogens, lanthanide, and actinides. You're going to fill in all the black boxes. That's going to be your second challenge question. The first challenge question is the metal cube question that we've talked about previously. If you're unfamiliar with that, review Chapter 2 problem solving lecture or talk to me in office hours or lab.